All right, so good morning. Thanks all for coming. And a special welcome to those who are here at this early hour, even though they partied all night at the DevOps party. And there's one gentleman up front here who's having a hard time, so let's keep the noise down so he can enjoy my talk. So say the next 15 minutes I'm going to be talking about software-defined radio. My name is Bert-Jan Schrijver. I'm a software craftsman at JPoint in the Netherlands. And in my spare time, I am also a Java user group leader for NL-Jug, the Dutch Java user group. So I'm curious, how many of you are members of a Java user group, for example, the London Java community? All right? Any members of the Dutch Java user group in here? All right, great. Both in the front row. I'm going to be talking about software-defined radio. I'll start with a short background, explain the concepts, then dive into ADS-B, which are signals from planes, dive into AIS, which are signals from ships. I'll talk about decoding these signals. There will be lots of demoing, and I'm going to be trying out the Q&A app that's built for DevOps UK. So if you haven't installed the DevOps UK app on your phone yet, please do it now. You can ask questions to the app, you can rate my talk. So let's find out how this works. All right, so how this all started. As I said, I work at JPoint, and at JPoint we usually work at our clients' locations throughout the year, so we don't get to see each other that much. So a few times a year we gather around with the whole team for a day of hacking and building fun stuff. And this can be stuff for clients, a proof of concept for something, or an open source project someone likes to like on, or just a fun project. And one of my colleagues, Roy, who's actually filming here at DevOps UK, he showed us some stuff. He brought from home a Raspberry Pi and some small USB stick and an antenna he built out of wood and copper. And his plan was to receive signals from ships. He ended up spending most of the day trying to compile the necessary stuff on his Raspberry Pi. But still, what he was showing was software-defined radio. And software-defined radio is a radio communication system where parts of the system are implemented in software. So usually cheap USB digital TV receivers work this way. It's just a small piece of generic hardware, and software does most of the work. There's a specific chipset, a Realtek chipset, which is generic enough to be tuned to a frequency of your choice. So that's anywhere between 24 megahertz and 1.7 gigahertz. It turns out there's a whole ecosystem around this kind of chipset with software-defined radio. So this is called Realtek software-defined radio, hence RTL SDR. By the way, does anyone know why Realtek is shortened as RTL? Realtek RTL? I've never understood it, but let's skip that. So all details you can find on rtlsdr.com. There are lots of cool projects there you can get started with for really a small amount of money. So these are the two kind of sticks I'm using. You can pick them up at AliExpress or DioExtreme. It's just a really small USB stick with an antenna connector. You plug it in and you're good to go. So as I said, there will be lots of demoing. So let's start right now. I'm plugging in my stick. And switching to a tool called GQRX, which is an open source software-defined radio listening tool. So this connects to the RTL SDR stick, and you can tune it to a frequency of your liking. So there are all kinds of signals in the air. Each one has its own specific frequency. One you might be familiar with is the frequency between 88 megahertz and 107 megahertz. Anyone know what there's at this signal? FM radio. FM radio. So let's see if we can find some FM radio here. 94.9. All right, 94.9. Should be somewhere here. Oh, that's not really a strong signal, but we're here with a lot of phones and Wi-Fi signals, so let's try something else. This is too good either. This one's stronger. So just listen to it a bit. Who likes classical music? All right, great. So, actually, that's a pretty well-known song, I think. That's that. Who was expecting this? There's something else I would like to show you, and as a matter of fact, I'm transmitting a wireless signal right now. Any ideas what it could be? Just shout. Mobile phone, yes, but it's there. Radio mic, yes. And I happen to know where radio mics are usually situated in the bandwidth spectrum. They're somewhere around 515 or, well, between 515 and let's say 550 megahertz. I also know that Antonio is presenting in the room behind me, so let's see if we can tune into his talk. That would be fun. Here's a strong signal coming on.
Any platform, any tooling.
This is not Antonio, I think, but it's still.
Now I'll code from now on.
So let's take some time to listen to this.
I'm going to use the terminal. I hope you can see it okay from the back.
Can you see the right there?
So you go to the internet, you download a zip.
This is Antonio, I can hear it.
You unzip, and it's ready to go. Under the bin directory, you have a shell called Forge, and if you execute this shell.
Okay, that's also. I probably should include him on my slides as co-speaker now. So thanks, Antonio. He knows I was going to do this, so he's all right with this. Okay, so far for the fun. Let's continue with the serious stuff. So these were two signals you can pretty easily pick up. There's other stuff. Amateur radio, guys with licenses to transmit a specific bandwidth is pretty widespread. This is something I recorded a week ago. Seems like these are some guys trying to fix a hard drive in a Linux computer.
We zien Windows niet meer in grub van Linux. Ik zit in de BIOS, Simon. Ja, oké.
So don't bother understanding any of what happened there. Basically the same thing, but on another frequency is communication between ships or boats or vessels to shore stations. So I live in the Netherlands, and I live quite near to a large channel, which goes from Amsterdam back to the rest of the world. And these ships communicate with stations on the shore to talk about where there are ships coming from the other side, whether they should go in the inside corner or the outside corner. So that's something here.
Boot achter de Maas, u gaat vlak achter die Fortuna het Merwe-kanaal in over? Ja, dat is wel de bedoeling. Ja, boot achter begrepen. Hoor, Hanna, zeg de Maas over.
These loud scratching noises are actually called, let's see, ATIS farts. That's the official term. It's a digital signal that's broadcasted after each transmission, which has identification about the device the sender is using. So this is just analog signals you can play with. There are also all kinds of digital signals. Who remembers the pager area before mobile phones were around? You know, you had these things and they were buckled to your belt and it would buzz and there would be a number on there. It turns out these are still used. And not by dinosaurs, but usually by monitoring systems. They have evolved a bit and they can now send text messages. So what you're seeing here is all kinds of messages. I picked up 4 pagers, and you can see all kinds of nagios and critical alerts in there. These things work pretty simple. Each message has a unique ID in there, and usually a pager only picks up the messages with its unique ID in there. But there's no way to block this, since you can just skip looking at the ID and look at all the messages. And then there's a different, this is called a POCSAG, which is the protocol for these pager messages. Then there's FLAX, which is another protocol for pager messages, and this is used by emergency services in the Netherlands. So ambulances, police cars have these little receiving boxes on their dashboard in their cars, and messages are transmitted to those cars. This is all open on the internet because there are lots of people doing this and publishing it on the internet, so it's not really secret stuff. So, I've been in this talk for, well, let's say 10 minutes. I promised to talk about Java. Haven't done yet. So let's start. How we can bring Java into the picture. it turns out there's a small utility called RTL TCP, which connects to your RTL SDR stick, and then opens a TCP socket where you can connect to, and where you can set frequency. I'm actually going to turn something on now for a demo later. So with RTL TCP, you can control an RTL SDR stick on the same machine on a remote machine. So you could also plug it in another machine and connect to it over the network. And this is pretty cool when you want to receive signals and do something with them in, for example, Java. So let's start looking into one of them. There are lots of planes above us, and planes are equipped with an ADS-B transponder. An ADS-B is a system designed for monitoring and collision avoidance, and reports identity of planes, heading, position, and more. So this system has been around for a while. It's an open system since planes from different countries need to be able to communicate with each other. And these planes are equipped with GPS receivers, so they know where they are. They know who they are, they know what their heading is from their compass, and they know what their speed is from their speedometer. And these signals are sent from plane to plane, but also from plane to ground station. So the control tower knows what planes are coming in. So now we got our RTL TCP socket. We got our Java IDE ready to connect to it. We can connect to it, but now there's this huge audio stream. Since the digital signal is represented as an audio stream, we need to process, but I got no idea how. There are some closed source decoders in Java. They're basically a jar you can download, put it on your machine, it connects to your RTL TCP socket, and then starts transmitting this data to some site on the internet, sites like planefinder.net, who aggregate all this traffic from all the world. So there are no closed source, there are no open source decoders. I'd really love to start tinkering with Java with it. So what can I do? It seems like I have no other option than to write my own decoder, which I really do not fancy, since there's all kind of difficult decoding stuff in there. No other option, or is there? We got closed source, we got Java, think evil. Any ideas? Of course, we can decompile the living daylight out of it. So decompilation is, in legal terms, it's a difficult thing. I have been looking into this, and it turns out that it's okay to decompile for debugging purposes. So when you have software from a vendor that can't support you anymore, you can decompile it to look at how the software works. It's certainly not legal to decompile Java code and then include it into your own product and ship it. So I'm kind of going to leave in the middle about what I did. But how does this all work? This is a picture of getting it all together. You start with an antenna. When you want to receive wireless signals, having a good antenna is key. And a good antenna is tuned to the frequency you want to receive. So for ADS-B, that's 1.09 gigahertz. And there are all kinds of plans online on how you can build antennas for this. So I built a small antenna with antenna poles that are tuned to, I think, a quarter of the wavelength of 1.09 gigahertz. I have no idea how to calculate this, but you can just look it up online and then do it. This connects to the RTL SDR device. There runs an RTL TCP server on my machine, and then I'm running a Java app which decodes the ADS-B signal, writes it into MongoDB. No specific reason, I like MongoDB, but it could have been anything else. And then there's a simple web app using Jetty and jQuery to build an API for that data and present it on Google Maps for viewers to enjoy. So I could have used any technology for this. I didn't want to make a point by using the coolest or latest or greatest. It's just about a simple API for the data which is in the database. So it's demo time again. This is the web interface of the application, just a simple Google Maps interface. And as you can see right now, you can see nothing on this map, since we're looking at the Netherlands, and we're not in the Netherlands right now. So let's zoom out, zoom in. Here's London. We're in London, right? And you can see some planes moving over London, but well, I'm receiving this with just this stick in this building with rooms above us, so the reception isn't too well. But still, we can see this plane wandering about London and is probably making a turn to go to some airport somewhere here. So, can you see it? Right. I'm going to show more later, so let's just take a look at this now. This plane is actually moving right now, and to prove that I'm actually receiving this, I've incorporated a link to an online site. This is flight AIC 1115, which should be above London at the moment, which it is, and you can see the curve here, right? So this kind of proves that it's working. Pretty cool, right? Yeah. Okay, so it gets better, because this morning, after I woke up, I put my antenna outside, and outside you can receive a lot more. So let's go back like 200 minutes, and this is what it picked up. And the cool thing is that you can see all kinds of patterns in here. So these planes come from here, where they start getting into range of my antenna, then they make this turn, and then they all gather around here, and they're all heading in the same direction. Any idea what that direction would be? Let's see if you're right. I think you're right, since Heathrow is here. So you can see all kinds of cool stuff by just receiving and analyzing this data. So how does this work? Let's dive into the details. I'll just be looking at the front end right now, since I'll talk about the back end a bit later. So let's see. It's a really simple web app with an index.html, which just has a few input fields and then a div where Google Maps draws on. And then all the magic is in a vanilla JavaScript file, just using a bit of jQuery. So I'm initializing the map here at the top, and creating a home marker where my home is. If you're ever in the Netherlands, you should really visit Utrecht, since it's a cool place. And then there's a function that performs a basic AJAX call to the backend API to fetch the position data. So how does this look like? I hope this is visible for you. So this is just a bunch of JSON, and it's basically a list of positions, where each position is a data for a specific flight. So here is flight number MON78GM, and I can open this, and then there's some general information like it's an aircraft, this is his ID, this is the timestamp where we last received this data, this is its current heading, and there's a list of positions in there, and which are just latitude and longitude coordinates. So by processing this response, we can draw on the map. So when the API response is received, data is processed, and this is just basically looping over all the data I get back, building a list of Google Maps let long tuples. So it's a Google Maps position object. Drawing a specific color when it's a ship or an airplane. I'll tell more about this later. And then draw a polyline, which is a Google Maps track, using the coordinates with a specific color. Removing the old track when it's already there to prevent drawing overlines. And then it's just a matter of drawing the plane icon, which is an open arrow Google Maps symbol. And here's a small optimization. When the marker is already there, I'm moving it. When it's new, I'm drawing it. Since moving is a cheaper operation than drawing, you'll see that when there's lots of data going on, you need to start doing these kinds of optimizations, since otherwise your browser won't be able to handle it. And there's a simple listener to when you click an object, it opens an external site with data. These are different sites for ships and for planes. So that's what I've just shown you. So back to the presentation. So any questions so far? Anyone use the app so far? Let's take a look. How much bandwidth does it have? Is there any hardware that receives 2 to 5 gigahertz, like receive GPS? Yes, there probably is. This thing is limited to like 1700 megahertz. So you would need another device that goes to a bigger bandwidth spectrum. So you can receive anything from 24 megahertz to 1.7 gigahertz, and that's it. But I haven't really looked into other devices. It's a very popular one. It's used for software-defined radio a lot. So basically, I stopped looking when I found this. I think it was cool enough. There was a second question. Could you start receiving confidential data? Yes. Well, it depends. It always depends. It depends whether systems are transmitting this kind of data. So ADS-B is an open system, which is designed to be open, since if you can't receive the collision detection signals from other planes, you'll probably run into them sooner or later. So I'm not sure what I would do if I was building Air Force One. There's two sides of the story. It could be good to send out these signals, since you know you're not going to bump into Air Force One, which you probably don't want to do. On the other hand, you'll be able to identify Air Force One. So I think the security aspect prevails here, and probably Air Force One isn't transmitting any ADS-B signals. Probably the collision avoidance system from Air Force One are a bunch of jet fighters surrounding the plane and shooting down other planes. So. Okay, so let's continue. That's all cool and fine and dandy, but running this in your house doesn't work too well. For reception of wireless signals, a line of sight visibility between sender and receiver is important, because when something is in between there, it's blocking, and the reception goes down pretty quick. It would be cool to run something that's always on, and I need this laptop for some contracting work now and then. So let's start looking into something a bit different. I live in a house. I have a small garden with a small shed in the back of it. And I love Raspberry Pis, and I think every project gets cooler the more Raspberry Pis you add into there. So I started by adding one. It's in my shed. Here you can see the home-built ADS-B antenna, and you can also see that I'm not an expert in soldering. But this antenna is on the roof of my shed. It's connected to an RTL SDR stick, which is in the Pi, and the Pi is transmitting over Wi-Fi. So the Pi is opening an RTL TCP socket. Then there's my Linux box in the attic, connecting to my wireless network to the Pi in the shed, and then broadcasting it on the internet, so you can receive it from the outside. But it turns out that the raw RTL TCP data stream is pretty big in terms of bandwidth. So I started with just a regular no-brand Wi-Fi stick, and it couldn't keep up with the bandwidth. I had to buy a specific high-performance Wi-Fi stick that could cope with the 30 to 40 megabit signal that was going over the line. And that's problematic when you're using Wi-Fi. So I was doing this talk a while ago in the Netherlands, and someone from the crowd said, so why don't you just decode the signal on the Pi itself? And that was actually a pretty good idea, so that's what I started doing. So you can use all kinds of tools to do this. And when you do this, you really cut down on the data transfer between the two sides. I would also like to give AIS signals from ships another try, since it didn't work. I tried it before I was looking into planes. I couldn't get it to work, and it wasn't because it was hard, but it was because I had no idea what I was doing. And receiving planes is easier since they're higher in the air. They're transmitting at a much higher rate, much higher bandwidth. So I'd really like to start looking into AIS. I also really want to ditch out the decompiled code, since it's horrible. So, second version. The image is almost the same, except for I'm now not using a RTL TCP socket on the Pi, but I'm using dump 1090. Dump 1090 is a small C utility which connects to the RTL SDR stick, decodes the ADS-B signal, and then displays it on a console, but also offers it on a REST endpoint through HTTP. So the decoding part moves a bit more to the Pi, a bit more to the C side, but this results in a lot lower bandwidth usage, since now the only thing that goes over the line is just JSON data, so it's at most a few kilobytes per second. So this is how the interface looks. it just consists of flight IDs, speed, heading, latitude, longitude, and some logging data about the signal and the number of messages it received. So now we can start looking into AIS. AIS is pretty much the same as ADS-B, but then for ships or boats or vessels or whatever you like to call them, those things that float on water and transport stuff. So AIS is also used for monitoring and collision avoidance. It's actually not the primary system used for collision avoidance between ships, because that is, just shout. Radar, yes, exactly, radar. So this is used as a supplement to radar. And there's two types of AIS. There's Class A, which is used by large freight carriers, which has a large range and transmits a lot of data. And there's ADS-B, which is used for smaller vessels, for pleasure crafts. It has a shorter range, and it also transmits a little less data. So these ships are connected with a GPS, so they know where they are, they know where they're heading, they know how fast they're going. They're transmitting AIS. This is used for collision avoidance between ships, but also for monitoring from posts on the shore. This is mainly useful when you're in a canal, for example, which has a lot of corners, and you want to see what's behind the next corner, for example. So how can we decode AIS? AIS is on, I think, 170 megahertz. And the pipeline for decoding AIS is similar to ADS-B, just using a different tool set. So again, we have a specific antenna, which is just two pieces of coax cable connected together in the middle. There are two pieces of 31 centimeters, and when you get them together, it's 62. And 62 centimeters is exactly the length of one wave on 160 megahertz. So when you tailor the antenna, your reception gets a lot better. So the antenna is in the Pi, and the Pi is running RTL FM, which is another utility from the RTL SDR suite. And RTL FM receives data and then writes it to a Unix pipe. So it decodes the data into an audio signal, and then you can process this audio signal with whatever you like to process it with. So I'm using AIS decoder from the guys at aishub.net. That's a site where maritime traffic is aggregated and presented on a map. And AIS decoder has the possibility to decode the signal into NMEM messages. And NMEM messages is a maritime standard for inter-device communication on ships. So, for example, when you have a ship, you usually have a GPS somewhere in the ship. You have a speed indicator somewhere in the ship, a depth indicator, maybe a chart plotter or a radar. And these devices talk to each other via NMEA. NMEA is a protocol over a serial bus with decoded messages. I'll show them in a minute. And AIS decoder also has the possibility to send the decoded signal, so the plain NMEA messages, over UDP to a UDP socket. So I created a small Java app which opens a UDP socket, and the AIS messages get transmitted to that socket. So the messages look like this. They're prefixed with AIVDM, which means, hello, I'm an NMEA message, and it's AIS. And then there's a decoded string, which you'll see decoded pretty soon. So to decode this, that's actually a funny story. I did this talk at Devox Belgium last year as an Ignite talk. So I was squeezing all this in just 5 minutes. It was really a rush, also for the audience, I think. But when I went back to my hotel after Devox, I was in the tram. And I met this guy there, and I was explaining him what I was doing with planes. And this guy said, well, that's funny. I'm doing exactly the same thing, but then for ships, commercially, for a port in Denmark. So this guy was Thomas Borg-Selling, who was doing commercial stuff with AIS for one of his contracting jobs in Denmark. And he pointed me to a nice library, which is called AIS Messages, which is an open source Java library you can use to decode AIS. So no decompiling here, yes. So putting this all together, is the same picture as you saw before, but then with ships in there. So now I'm decoding AIS using dump 1090. I'm decoding ADS-B using dump 1090. It's JSON over HTTP. I'm decoding AIS using AIS decoder, and that results in NMEA over UDP. The Linux box is still in the attic. It's all connected through Wi-Fi, and it's available on the internet. and the data traffic is really low. It's set at most a few kilobytes per second. So, demo time again. I'll now be connecting to my computer at home, which is running a website connected to to the Raspberry Pi in my shed. And this is what it's displaying at the moment. So this is data from the last 15 minutes. So I live here near the center of the Netherlands. Amsterdam is here, where Schiphol is. And you can see all kinds of flight paths forming. These are planes ascending here and then moving above Hilversum, then go away here, and they're here going south. And when we increase the history, you can see that there are bigger flight paths forming. So I can switch between just ADS-B data, where I see planes, or I can go to AIS data from ships, and I need to zoom in to visualize this. So this is the Amsterdam-Rijn Canal, which is a large channel going to the Netherlands, and you can see that there's ships over here. And this is actually from the past hour, so there are quite a few ships crossing there quite close to each other. I can look into some of these ships, and I will be redirected to a site that monitors marine traffic. So this is the Ijuna, which is a tanker which has just passed by my house. So what would be fun to look up here? I came here by plane at Wednesday night. So I was with the British Airways 433. So let's see if we can find it. Well, it certainly wasn't here in the last 60 minutes. So Wednesday night, that's like a few thousand minutes from now, right? Let's try 3. So here I am, sitting in the British Airways 433, and I was last seen at Wednesday 18:13, which is close to 15 minutes after I took off. So this proves that I was here by airplane, or not, depending on how you look at it. So that's all pretty cool. I'm sure that you would like to know how this all works. So back to the IDE. I've shown the front-end part. So the back-end part is actually pretty simple now. The API I'm not going to show, since it's just a plain API which fetches data from MongoDB, filters it, mangles it, and then sends it back. And there's 2 connectors, one for ADS-B, which has a source which I'm using to abstract over multiple sources. So I could extend this with other kinds of sources. And this source starts a dump 1090 client and fetches data, and this goes into a loop. So this client just builds a basic HTTP request to dump 1090, then maps a JSON to a domain object, adds a timestamp to it, and adds it to a list. So this is really simple, basic HTTP communication. For AIS, it's the other way around. Since we're receiving data now, we're not connecting to a socket. So there's a source here, which opens a UDP socket, and it continuously receives UDP packets here and then feeds it to a AIS decoder. And here you see the AIS messages library in play. So the NMER messages are received, then fed to AIS messages, converted to a domain object, which is called position data. I'm just here copying the properties from the AIS messages domain object to my own domain object. So that's basically it. Any more questions so far? Yes, there are. Let's see. We've handled Air Force One. Any publicly available PSN ports attached to USB devices where anyone can receive data from a remote antenna? No, I do not know of them, and I think they would be overloaded quite soon, since you can just only tune to. Yes?
Yes, there is such services.
Ah, there are. Okay, cool.
They use not such small sticks, but wideband receivers,
yeah.
And there is about 5 or 6 on the internet. It's more like the user interface you show first,
yeah.
But on your browser.
Ah, cool. So it's basically.
I don't remember specific addresses, but if you search for wideband internet receiver, Google it.
Okay, so
it could be found.
My answer was wrong. It turns out there are these kinds of services. You can search for wideband wideband receiver, you said?
Receiver.
Yeah.
Internet.
Wideband internet receiver, and there are some publicly available services where you can do this. You probably have to pay for them, I think.
No,
oh, they're open. Okay.
It's, they are overloaded.
Yeah. They use a lot. So, well, you can also pick up one of these sticks for like $7 at Alibaba.com, so you can play with it yourself. These sticks are limited to receiving one frequency at a time. Do you do the digital signal processing in Java? How easy is it when you don't have unsigned integers? Well, I was doing this, but I stepped away from this since there are pretty good lightweight C implementations of doing the signal processing. So I'm just I went the easy way and started using those readily available implementations. I did take a look at the decompiled code, which was pretty horrible to read and understand. There was all kinds of tricky bit shifting going on there. So
I'm doing this.
All right, well.
I could show the demo on my laptop after this talk.
Okay, cool.
I have some open source project, which is not open source yet because I don't think it's good enough to show to people yet.
Yes, okay, but excellent. So there'll be more on this later. If you want to share any information, just let's tweet it with the, let's see, with the hashtag for my talk, and then we can continue discussing it on Twitter. So far for the demo. Now I have this system running at home, and it's filling up my MongoDB with data from planes and from ships. So what could we do with it? We could start playing with it. So let's start looking at the antenna range for planes, which is, I think, quite impressive. It covers most of the Netherlands. For reference purposes, I've put London in the picture too, so you know how big the Netherlands is. Not too big. And it covers most of the Netherlands by just using really basic equipment and very little tuning. I've soldered together this horrible beast of an antenna, which is just sitting on my roof or sometimes in my attic near the window, and still receives data from that's at least 200 kilometers away. I've done no tuning whatsoever on the signal. You can do shielding on your cables on your receiver to improve signals. So even with very basic stuff, this is the range you get. For ships, it's a lot less, since these signals usually don't have to travel from a few kilometers up in the air down to the ground. So these are transmitting at a lower power. But still, I could get a few kilometers of range by using a basic antenna. And it's not really too high up in the air. If I would put it on a stick and put it on my roof, so it would be 10 meters above my house, I would be able to receive more. I won't be able to receive my neighbors again at my house, I think, because they wouldn't really like it. So what's interesting here is that you can also see there's a small harbor just down here. You can see some ships being docked here for transferring whatever they're carrying. So, of course, the interesting thing to look into is aircraft, since these produce more data and it's easier to get. So here's 1 hour of data. I made these screenshots yesterday afternoon. So this is the planes that were in the air yesterday at around 2 o'clock in the afternoon. So this is 1 hour of data, and you can see some flight paths forming already. So you can see here they're going this way. Here there's a few flights going this way. When we continue increasing the range, you can see some more of these flight paths forming, but also there'll be some more disturbance in the picture, since there are all kinds of planes just shooting over the Netherlands. We go to 4 hours, there's a bit more. We can jump to 8 hours. There's already not really much to see anymore. 16 hours, and that's not really a big difference, 8 and 16. But this is probably because I took these shots yesterday afternoon. So when you go back 16 hours, you end up somewhere in the night. And in the night, there are usually less planes than during the day. So we can increase this to 24 hours, and then we should see something different. Yeah, so that's just 24 hours of data. That's a lot of planes crossing above your house. So, to summarize, software-defined radio is fun, and you can get started for just a few bucks or even a few pounds. Go to DRXstream or AliExpress and just order the SDR sticks that are ordered the most, because these are probably good. If you want any details, you can go to my GitHub page, where all the software I've shown you is on there. There's instructions on how to configure Raspberry Pi. There are links to AliExpress and the Extreme where you can buy those sticks. There are even instructions on decoding pager messages, stuff like that. Be aware that not all of this may be legal in your country, depending on where you are. There's a live demo you can enjoy while it lasts on ser.revolution.nl. I think if 10 or more of you will be opening that site, it will not be too responsive anymore. So let's just see if we can burn my machine at home. I'll phone the missus that she'll have to be ready with the fire extinguisher. And there's more information available on rtlsdr.com. There's all sorts of cool projects there you can play with. So there's time left for Q&A, actually a few minutes. So let's open the site again, which is still here. We've had this, public available piece, digital signal processing. How can you differentiate between types, commercial, private, and government? Well, as usually, it depends. The only data you receive is an identifier for a plane. So for a plane, it's ICAO code or the flight number. For a ship, it's its MMSI number, Mobile Marine Ships Identification, I think. So you can look this up on the internet, and most of them are already available. So you could perform a lookup to a service that offers these kinds of conversions. Other than that, it's just a standard signal you receive, and you won't really be able to differentiate between types. I think fighter pilots do not send out ADS-B messages because that would be kind of easy. So question there, yes?
There was an article on Hacker News the other day that, well, a lot of corporate jets, you can look up the call sign because that's public information, and then you can see like where the Google corporate jet has been flying.
Yeah.
And there was a website for looking these things up that was blocking them because companies were worried you were going to say, oh, I see a lot of people from Google have been flying to Russia, therefore I know where their next expansion plans are.
Yeah, yeah.
So you can recognize commercial flights and private flights a bit like that, I guess.
Yeah, actually, so the question, or rather the statement was that it has been on the news recently that since these flight data is already readily available, you can look up these flight numbers and call signs on the internet and see where, for example, the corporate Google jet is going. But you don't need software-defined radio for that. So the site I've shown you, planefinder.net, has all this information. So indeed, you could find out which are the flight numbers that the Google corporate jet uses, or the Apple helicopter or whatever, and see where it's going. That would actually be interesting to do. It's another topic, but still interesting. Question there?
So one of the fields on your ADS-B decoder was the squawk code.
Yeah.
That can be used to tell the type of traffic, whether it's commercial or military, police, whatever.
Excellent. So I'm learning as we go. The squawk code, which is in the signal that's received, can be used to distinguish for the type of planes. I've always wondered what this was and never looked it up, so thanks for that. Yes?
Can it be detected that you're doing this? I mean, for example, if somebody passes it, oh, you're not allowed to do that 10 miles around any airport, could it be detected?
Yeah, the question is, can I be detected doing this? For example, when it's legally illegal to do this? Well, yes and no. You're just I'm doing passive scanning, so I'm just receiving signals that are in the air anyway. That is something that cannot be detected. But of course, when I'm driving around at the airport with my laptop on my lap and an antenna on my roof, you can be detected. So it all depends. But it's specified. I'm not transmitting anything. This stick isn't even able to transmit signals. You can get, for a few bucks more, you can get sticks that can transmit. But then you would have to probably either use a frequency that's free to use or have a license to transmit data. Yes?
Can you pretend to be a plane easily?
Question is, can I pretend to be a plane? Yes, I think you can. If you would have a dongle that is capable of sending signals. The specifications are open, so I think it will be pretty easy to do so. I'm also thinking it will be pretty not so much legal to do so. But probably you can. But there will be a problem there, since you would have to have a pretty high volume or high power sender, since otherwise no one will be able to receive you. It's just you can receive it yourself in your home. It should be fun for playing and pretending you're playing. But I think you need serious equipment for this. And when the airport police sees a stable plane signal coming from your house, I think they will send someone in there. So. There's a question. Do you also receive LTU data? Could you incorporate this in your app? Yes, that's a good question. And yes, I am receiving this. So it's here. I think this is in meters, probably, because feet wouldn't be too high. And yes, I've thought about incorporating this. I haven't done this yet, but I could do it maybe with the color of the line or the thickness of the line. What you're now seeing is that signals are just being cut off at a certain moment, and that's just where they go out of range. So let's go into a situation above the Netherlands, and then you can see. Let's see. You can see planes going into. It's getting heavy already. You can see planes going into Schiphol, for example, and then just bumping off the map. And this happens when they get too low for me to receive, so that there'll be something between the aircraft and my receiver. So it seems like Firefox has decided my session is over. Let's try again. Let's see if you have any more digital questions. Have I tried to decode satellite images? I haven't, but I have been hinted that this is possible. It's just another signal, another frequency you can receive, and then you have to look in the specifications for this and how the signal is built, and then you can start receive it. But most of these patterns are documented pretty well on the internet. And lots of times there are already projects doing this, so you can just grab something and start looking into this. Any more questions? I think you were first.
Why are you doing this? Are you just playing? Or?
Why? Yeah. So the question was, why am I doing this? Am I just playing? Yes, definitely. I'm usually working on serious stuff, also cool, but stuff like continuous delivery and DevOps for our clients. And sometimes you just need a break from the serious stuff and do something fun. And this is it. This is just a hobby project on the side that I've worked on for a while. So just the short answer would be, why are you doing this? Because it can be done. So. There was a question there?
You mentioned sticks that can transmit as well.
Yeah.
Can you buy them on AliExpress for £10?
No.
Or are they?
No, it's several $100. Google Hack RF, for example. Hack RF. It is one of the cheapest two-way devices.
So the question was, can you buy these sticks that can transmit? For £10. Answer is you can't. They're several $100s. But when you start looking into that, you really need to be careful with what you transmit and on what frequency, because I think there'll be a van with nice flashing lights on top at your house pretty soon. Yeah. So we got like a minute left. Any more questions? Yeah, sure. Let's see what's going on in the room next to us.
Yeah.
We can see.
It's even more interesting when he's finished.
I have this generate forge shell that I've created. If I open it, I have all the commands. So here I'm creating a project called Project JSF with a speaker, an entity, with a name, a surname, constraints, dates. Look at that. A one-to-many relationship.
All right. So feel free to continue listening to Antonio. Thanks for your time, and I'll see you around.